And off we go, Andrea. It's all yours.
Okay, can you hear me? Yeah.
Yes, perfectly well.
Okay, thank you. Thank you very much for having me here and giving me this opportunity to present. So I'm presenting this paper with joint work with Francesco Ravazzolo and Luca Rossini. The paper is called Integration of European Electricity Markets in a Reverse Mixed Frequency Panel. Oh, okay. So this is, we have an econometric question for this paper. And for this question, we developed a new method, building on some important results in the literature of electricity and the mixed frequency data. So our problem is this. There has been a lot of turmoil recently concerning the war in Ukraine, the COVID, and everybody knows that a large increase in the price of the gas, for example, happened after the outbreak of the war in Ukraine. And this surge in prices is has only lightly revealed the absence of a common European energetic policy. So in general, the integration of European electricity markets is an objective of European Commission since 2014, but there has been little progress has been made since then, and there are still national regulations at the national level, and that are still in force. So in general, no progress has been made since then. We want to actually measure we want to measure the integration across European markets concerning electricity prices. So we want to see if there are differences in the energy mix of the European countries. So this is an econometric problem, and we develop a methodology for this. To give you a little bit of overview on the data we use. So here I consider, I plot the electricity prices for Germany since January 2019 up to October 2023. I smoothed the electricity prices with wavelet analysis, and I reconstructed the signal with the low frequency component to just to show the main signal from electricity prices, and then I average it over the days, and then I also considered the coal and gas prices, which is a unique price for all countries because it corresponds to the price of futures traded on international exchanges. And as you can see, the correlation is very strong, and we will exploit this correlation in our model. Here, I consider instead for Italy. These are data about Italy, and here I consider these violin plots where I show the distribution for each hour of the day of the electricity prices, for the electricity price, for the forecasted demand, the solar and wind production. So in general, I think this figure is nice because we can see that there are very important patterns through the days that have to be considered when modeling electricity prices. In particular, you can see that the solar production forecasted demand have peaks during the days, and instead these patterns are less evident from the price and the wind, which should be further viewed also on a monthly and hourly point of view. So for this application, so this is still an ongoing project, so we still don't have the application ready. But in general, we have this data from Refinitiv about 10 European countries, which are do not only belong to the European Union, but in general European countries, because, for example, we have also data about Switzerland and Norway. So in general, we have these daily commodity prices about CO2, coal, and gas. So we have data. We have daily prices for commodities, and we have hourly prices for electricity, and then we have the hourly production of the renewable energy sources, so the hydro, solar, and wind production. In general, what we want to do is to observe any difference across country by hour and by country in the effect that each of our predictors, so the commodity prices and the renewable energy sources, have on the electricity prices. Any deviation from a situation of full integration is measured in terms of a different energy mix. So in general, we will quantify any deviation from full integration. Okay, after this quick introduction, just to show you what is the problem, I can quickly go over the literature, go through the literature. In general, there are several approaches that we consider to model electricity prices. Most of them rely on univariate models to model individual hours of the day, and perhaps with time varying volatilities. In general, these models consider gauge type specification, or they consider daily averages of the prices, which, however, are not good from the point of view of practitioners, because they don't get the prediction for the hourly series of the prices, which is what is of main interest for them. And more recently, there are also there have been considered also approaches which take into account any dependence across the hours, which is very important, in fact. For example, the paper in Maciejewska and Nowotarski, and in the paper of Gianfreda and Coders. So in our paper, we take a different, I would say, we consider the reverse and restricted Midas model proposed by Foroni, and we adapt this to our framework, in which we have mixed frequency data. And then to consider interdependencies among countries and across countries and hours, we consider the Bayesian Markov-switching panel of Casarin and Coders, which in fact is the peculiar feature of our model here. And to introduce the example, I consider a very simple specification. In general, this model is very parameterized, so I just consider here a very simple example. So we have this linear model where the electricity price is denoted by Y. This is the electricity price for country G at time T plus H, where T is the day and H is the hour of the day. Then by X, G1, T plus H, I denote a daily covariate. And with X, G2T, I denote, for X, G1, T plus H is a hourly covariate. And then the daily covariate is denoted by X, G2T. And this is a mixed frequency model because we have a lagged dependent variable, YG, T plus H minus 1. And then we have this hourly covariate and a daily covariate. These are coefficients that change depending on the state of the market. This state, and we denote the state with the state variable SGT, which depend on the country and changes over time, but only over the days and not over the hours. Okay, in general, the model is again a mixed frequency model, so it can be represented with these lag polynomials in the dependent variable and which is alpha, and beta corresponds to the lag polynomial in the low frequency covariate. So this is a daily covariate in our model. In general, with no loss of generality, we may include here also high frequency predictors. I didn't include them to show like the model is already shows a very heavy notation. So in this case, I exclude them. The variance of the error term depends on the country, changes with the country and the hour of the day. In general, this model is very flexible because you may allow also for different kind of dependence. And so we call this model a Markov-switching reverse unrestricted Midas panel. As I mentioned, the parameters in our model change and follow. The parameters in our model change according to a state variable whose evolution is governed by a Markov chain with transition probability, which are given by P, G, L, K. So this probability are equal to the probability that the state is equal to K and at time T, given that in time T minus H is in state L. And in general, this state variable run over the days and not over the hours. So the switching coefficients are defined as through this indicator variable these variables psi, which are equal to indicator variables to be in the kth regime. So, for example, from the intercept of the model mu gh, this is the sum from k for k that goes from 1 to k, which is the number of states of this psi times mu. So in the case this is equal, when this is 1, then we have a regime-specific intercept, a regime and hourly and country-specific intercept. And it's the same for what concerning the autoregressive coefficients and the coefficients on the explanatory variables. So the very peculiar thing of this model regards the cross-dependence in the panel. So the cross-dependence across the hours and the countries. So we exploit this methodology proposed by Casarin and co-authors in 2018, where we model the country, hourly, and regime-specific parameters, so the intercept and the coefficients, as the sum of 3 different components, where the first one is we call it actually Casarin and co-authors call it a common factor. And then we have random effects. So this is the common factor because it is the component that only which is the component of a certain regime for a certain regime. And then the intercept is made up of 2 further components, where the first one is the hourly random effect. This hourly random effect is homogeneous across countries, but changes depending on the hour of the day and on the regime, while this Z is the country random effect. So it is homogeneous across hours, so it's the same for each hour of the day for all countries, but changes depending on the country and on the regime. So this way, we are able to introduce cross-dependence in the panel very easily. It's very flexible because you may also assume to allow this intercept to change also, for example, depending on some covariates, it's very, very flexible. For example, Casarin and co-authors also have another component here, where they indeed make these coefficients also depend on an explanatory variable random effect. So we show in the working paper that this model has a convenient representation, which I call it the compact form of this model, but in general, it's just an algebraic results, which allows us to rewrite this model with the predictors in the explanatory variables in this vector Z, and then we group all the coefficients in gamma, and the random effects in Z and psi. So we have in Z we have the country random effects, and in psi we have the hourly random effects. What we have a nice result that I do not show here for reason of time, but we are able to marginalize out the random effects in this model, so we can put these random effects in the error term, so that this model becomes a model with time varying variance, and this is very important for concerning MCMC sampling, because without this with this raw-black dualization strategy, we would not be able to employ an efficient MCMC sampling algorithm. So in general, the posterior is not analytically tractable. This is the expression for the posterior distribution for inference. It's not analytically tractable. I also skipped the part concerning the priors. If you have questions, you can ask me. In general, we impose very, very standard priors. I think I only forgot to say that for identification of the regimes, we would like to allow the parameters to change depending on the state of the market. So we are considering two regimes, a high volatility and a low volatility regime. So in general, we will put restrictions on the volatility. So back to the posterior. This is not, as I said, analytically tractable for the posterior approximation. So we rely on MCMC for GIP sampling. So the structure of this GIP sampling algorithm is quite involved. So there are two main steps for the GIP sampling. Firstly, we draw a portion of the parameters, and a portion from the, we draw the two sets of parameters from the full conditional distribution, and exploiting the result from the raw black wellization, where indeed we marginalize out the random effects in the error term, we are able to add a collapsed GIPS step within step one. So we first sample the parameters psi, gamma, the probabilities of transition, and nu, and then we sample the random effects separately from the full conditional distribution. So this is what we have developed until now. So we want to apply this model on a data set of electricity, commodity, and renewable energy sources, for which we have data concerning both EU and non-EU countries. We have 10 countries in our data set. We want to quantify the impact of the commodity prices and RES on the country electricity prices, and this is good for estimating, for measuring integration across European countries. And maybe for future work, we are also considering to reset the model with a LiDAR structure and consider it for some forecasting application. So I hope you like my talk, and I'm done. Thank you.